Hello, in this tutorial I'm going to show how to design a common source amplifier by using the GMOD methodology. So before going to start, let's set the design specification. Set the DC gain at 20 dB and set the uh, GBW at 100 megahertz. Let's set the load capacitor is 1 picofarad. Then VDD is approximately 1.5. Well, all the specification is set. Well, and then I'm going to create a schematic for NMOS to extract the NMOS parameter or the lookup table or gem over ID lookup table. So that's the library manager. I'm going to work in this library. So let's create a cell view. I'm going to using 45 nanometer technology. So NMOS on board. And then analog leaf. And then set the parameters for length. I'm going to set the variable length, so ln, keep it your own choice. I'm going to set the wn. Okay, okay, all the variable is set. Then launch the ADL and I copy from the cell view. Initially set the length is 45 nanometer and width is 2.5 micro, VDD is 1.5 and VGS is in 0.5 500 millivolt. Okay, let's set the DC analysis, save DC input point. I'm going to sweep the gate voltage, so VGSN is 0 from 1.5. Okay, before going to run the simulation, I have to set a file to save all the NMOS parameter. So simulation file, uh, it's an SS file. So here I already created a .ss file, and I'm going to show how to create a SS file. It's very easy. Here is my SS file. Let's just copy and paste, and always remember, before going to save, make the extension which is .sh, and then save. Then it will be create a SS file. Okay, and then after that, just include the SS file. Here I include, then run. Let's check the browser. Yeah, you can see all the DC operating points for the NMOS is given here. So before first of all, I'm going to plot the GM over ID versus uh, GM over GDS. GM over GDS means the intrinsic gain. After that, I'm going to set a calculation. As I said, the GBW is 100 megahertz. Let's find the GM. GM equals to 2 into pi, which is 3.1416 into 100 megahertz GBW divided by load capacitor. So this is our GM, which is unit is microsiemens. Find the GM. Well, and then as we know, the gain AV equals, for a common source amplifier, AV equals to GM1 divided by GM1 plus, sorry, GDS1 plus GDS2. This is the formula for the gain of a common source amplifier, and for this case, which is greater than 20 dB, for, as I said, the specification 20 dB, that's mean linearly it's 100. So let's assume the GM1 equals to GM2. It's approximately GM1 equals to GM2. As it is GM1 equals to GM2, so we can find the AV equals to GM1 divided by GDS1, but as it is equals, so it will be multiplied by 2, so 20. So we find the GM. Let's AV equals to GM over equals to here is 20. Let's approximate it by 25, which is intrinsic gain. Okay, the unit of gain is voltage divided by voltage. Okay, the gain is set intrinsic gain, which we get 25. Okay, after that GM over ID is the GM over ID, that's in calculator. Then I need the intrinsic gain, which is GM over GDS. So first find the GM. The GM GDS is divided, so this is basically the GM over GDS. Well, after that I need a function. In x-axis GM over ID, y-axis GM over GDS. Apply. Let's set it to the ADL input. So the function, yeah, here is the GM over ID and here is the intrinsic gain. Okay, after that I need GM over ID versus ID over W. So again there's another option. ID and ID over W is ID over W, GM over ID versus ID over W. which is GM versus AV, and this is GM versus ID. GM over ID versus W. Okay, first let's plot the GM over ID for some lengths to find which lengths meet our intrinsic gain. So I'm going to parametric analysis length which 60 nano to so 45 nano to 500 nano. So 15 step. So here in a y-axis has the intrinsic gain, and here x-axis the GM over ID. So let's find which length meets our gain. So click on H, so horizontal line, and our expected AV is 25. So find 25. Okay, 25. We can set which is 7.75. Is 45. This is the 101 nanometer. This 75. If I set the 70 nanometer, it will be okay. Here's a you can approximate, you can get the maximum gain from here, which is basically the moderate inversion, and this is the weak inversion, and this is the strong inversion. I'm going to set the minimum length, but it has some drawbacks, like it's too much channel modulation, and that affects my gain. But for this tutorial I'm going to set that 70 nanometer. So length L1 which is 70 nanometer. Okay, we get the length is 70 nanometer. So after that, set the length is 70 nanometer. Then run the simulation for ID over W. Also, as I get the length is 17 nanometer, I can't measure the H25. So our GM over ID is 4.5. Let's set GM over ID is 5. We get the GM over ID. Get 5 Siemens ampere. Okay, it's fine. The ID, click on V, set the GM over ID 5. The 162. So ID over W is 162 microampere divided by micrometer. Let's find the W. As I get the GM over ID, let's find the ID. ID equals to GM is 628 divided by is 5, 125 microampere. So W equals to ID divided by ID over W. This is the length and width for our driver MOS. Okay, our driver MOS length and width is we get, and then I'm going to work for the load MOS, which is PMOS. So again I have to set another schematic for PMOS. So let's set it BGS VDD, set WS LP WP. Okay, all the parameters set. Then launch the ADL, load the variable. Initially I set the length is 45 nanometer and WV is 2.5. Micro, it is 1.5. BGSP is 0.5. DC, this is the design variable, that's the BGSP. Again I have to set the simulation file for the PMOS. For the PMOS, just change the name NM0 to PM0. I already create another .scells file for PMOS. There's no change, just I change the, I can see you that let's see what is the change. Here's only change NM0 to PM0. Okay, just click the DC operating point. Yeah, here's all the PMOS parameter. So what we need here, so I need GDS versus let's set again just parametric is close, close, Well, before going to calculate, let's find what is the GDS for PMOS. As we approximate, the AB equals to GM over by GDS is greater than 20. It's not 20, it's greater than 25. We said the 25. Approximately 25. Okay. So what is the GDS? GDS equals to GM by AV. So let's find the GDS. GDS is equals to GM divided by AV. So which is approximately 25. It's also 25. It's okay, which is also Siemens. And let's find the GDS by ID. GDS by ID. So GDS is 25 divided by ID. It's 125. It's 0.2. Well, I need to plot. One is the uh, ID over W, because I'm going to find the width for PMOS, and uh, GDS by ID. So let's first to plot GDS by ID. Let's go into calculator. So OS, and click here, find the GDS. Here's the GDS. Yeah, GDS and OS. Just ID, but I'm going ID is negative, so we have to absolute value. Okay, so here is a function error. Again, GDS. Let's get in the stack, and then ID. So GDS by ID, let's send in stack. After that we need ID again, ID stack over W. Here is the GDS ID, is the ID over W. Yeah, in a y-axis, this is the GDS over ID, and here's the ID over W. Or we can set the x-axis in GDS by ID, it will be better, and y-axis is ID over W. Okay, let's send it to the buffer, and for the we set the 70 nanometer. Well, H, so GDS by ID and ID over W. Here's the problem, is the PMOS ID open. Is the absolute of ID over. Let's check the function again whether is a problem or not. GDS over ID. Oh, let's or GDS over ID is 0.2, so 200. That and our ID over is W is 136. I think there's might some problem in this function. Let's check again. Oh, is for NMOS, by the way. Yeah, now it's okay. Switch. So what is this? 0.2. 0.2 means the 200 milli, and the current is 78. Here is I find some problem in function. You can see here which is the problem. Open. Here's the absolute value for ID over W, and y-axis with GDS over absolute of ID. Before I set the absolute value for whole function here, and then I solve that, and then I get the appropriate figure. You see the before figure we get the millivolt range. Yeah, this figure is also okay. Here I said the GDS is in x-axis and GMO ID is y-axis. That's why uh, I confused. By the way, no problem. Sorry for the confusing part. So let H is 200 and 78. Let's set ID over W. ID over W. We get what is 78. Let's set it 18. Now the W for 2 or the PMOS, writing PMOS, W for NMOS, length for both. So ID divided by 18 is 1.57 micrometer. And let's say it is 78, which I get from the curve to approximate. Well, I get all the parameters for both NMOS and PMOS. Let's draw the common source amplifier schematic. Just close or save the state, which is for NMOS or PMOS. PMOS. And then close this schematic. Also save. This is for NMOS. Well, let's draw the schematic. See, it's not my library, not tutorial. Yeah. So first the GDP45, then NMOS 1 volt. Set the NMOS, PMOS 1 volt. It is in common source. Or we can set it to, well, let's set the W and L parameter. The length is, which I get, 70 nanometer, and W for NMOS is 0.78 micrometer. This is in micrometer. 0.78 micrometer, or 780 nanometer, 780 nanometer. Well, now this is also 70 nanometer, and finger width is also 1.61 micrometer. Well, now for the common source amplifier, I have to bias this NMOS. So to bias this NMOS, so I have a current source. Here is the input, which is let's set the bias current, which is 125.6 125.6 or no, 26 microampere. Well, the bias current is set. Then set the load capacitor. Well, uh, we bias the NMOS and driver MOS. And how can we bias the load MOS? We need another current mirror by the as it is in current mirror. Okay. I need another NMOS. The label. And then to bias this circuit, make it is a diode connected. Okay, this for the same with length width, and this current mirror same length width. Well, 126, all is okay. Let's set VDD at the top. Cell is 1 picofarad and IDC GND. Frequency, the DC voltage 8 125 milli, and AC magnitude is 1, amplitude which is 1 milli, frequency is 1k. Okay, then I need a DC source. Separate the DC source. Let's look better. 1.5. All the parameter is set. Check save. This oh, and short the source and drain. Another where that's the problem. floating. There is a 0 or okay, all is set. Let's launch the ADL, and then first analyze the DC analysis. Then the DC operating point. Let's run. Let's see the DC operating point of this. So file. Sure. Well, all the MOSFET in saturation region, but this MOS is not. So let's find which biasing voltage this MOS will working in a saturation region. Parametric analysis. Is 0 to 200 500 milli 20 variable. Yes, so we can see before that 9 and 2, the 100 milli board. So if we set in the 80, this will be in a saturation region. We set it 100. It is in weak inversion region. The GM is 3.31. The GM is 4. We calculate for 5. 6. 6. By the way, let's see. It decreases the GM. So the 100. Well, let's for the AC analysis. This is a 110 to 10 giga, and okay, gain and phase. Yeah, the gain is 7.12 dB. It's not meet our requirements, but you can see the GBW, which is approximately 10 gigahertz. Let's 100. They were 11. So our gain bandwidth product is meets it's higher than our expectation, or but gain is not meet. It's 7.12 dB. We calculate for 20 dB. Let's set 5. What's the difference? See, it decreases the gain. Wait, 0.86. So as we assume all the parameters in weak inversion, and the length is quite low, as it is a 70 nanometer. That's why there's too much difference between our approximation and the results. If I show the transient analysis, for the 10, we plot it, select design. net 8, give the net name so we can easily uh, it amplifies. Well, the gain is quite low, but last time I designed another console so where is I get the high, not expected, but it's quite high rather than it, so I can show. Well, that's same. What's the problem? Tools, plot, gain and phase. I choose the input is first, that's why it's in negative. Let's again plot, gain and phase. Let's choose the output and then input. Yeah, here is the 13.6 dB, which I estimate for, uh, as I remember, that 20 dB. So this is not uh, bad, but in this design in which I make in tutorial, here is a quite lower gain, but you can see here uh, this also makes the GBW requirements. So actually this takes time to design a good analog circuit. For this case, I show uh, this common source amplifier, but you can easily calibrate it and optimize it by vary the length and width after primary calculation, and then that's you can meet the requirements, I hope. Okay, thank you for watching this tutorial. I hope I will make more videos